So hello everyone, very nice to meet you this afternoon. So I'm Mohammadreza, Aghaei, coordinator of the COLLECTiEF, and today I'm just providing like a recap what we've done so far and what is the next step of the COLLECTiEF, and then I will provide some also overview about some works we are going to do after ending the project. So we are 15 partners from 6 countries and running for 4 years. So we are in the fourth year, and we have a 4 urban pilot located in 4 countries. So as I said, we are 15 partners from 6 countries, and 11 partners are from industries, and we have 4 universities. So here is our team and our expert from different organizations. Most of them, as I said, has experience in the industrial side. So our objectives at the beginning of project was to create the collective intelligence-based energy flexible network with the low-cost installation, maximum data security. And also we wanted to have a cost-effective component available in the market in order to provide cheaper solutions. And we are testing our solution in the 14 pilots in 4 countries with the different climate zones. And we also want to achieve more accurate and non-invasive environmental monitoring through sensors focusing on the user needs. And we design also the smart, user-centric, and user-friendly platform in order to improve the building management and maximize the energy saving. So I would like to invite you to watch the first video of our project just to understand better about our solutions.
75% of the buildings in Europe do not use their energy in the best possible way. They are not as smart as they could be. Currently, only a small number of existing buildings are smart, meaning they can adjust to the users, to the climate variations, and to the needs of the 75% of the buildings in Europe do not use their energy in the best possible way. They are not as smart as they could be. Currently, only a small number of existing buildings are smart, meaning they can adjust to the users, to the climate variations, and to the needs of the energy system. By following the principles of collective intelligence, we can upgrade and democratize the smartness levels of existing buildings. And we can do that at a low installation cost. In brief, through collective intelligence, we will smart up your appliances and heating and cooling systems while lowering your energy bills. What is collective intelligence? We can see great examples of collective intelligence in nature. Birds, fish. When alone, they find themselves limited, but when they move in groups, they help each other to survive continuously changing and sometimes dangerous environments using simple communication techniques. In general, they are stronger together rather than alone. Through collective intelligence, the interaction among individuals creates a greater smartness at the group level. Thanks to our user-centric platform, at COLLECTiEF, we create a community of smart buildings, in which each one of them becomes an active element of the energy grid, generating benefits for the entire building community. This is how we make buildings and energy systems in urban areas more efficient, smarter, resilient, and greener. With COLLECTiEF, we will bring all European households into the 21st century. Learn more at collective-project.eu and follow us on social media.
So thanks for watching. So how it works, actually the collective intelligence is the main part of the fundamental of our projects, and the whole actually structure of the projects, including the edge and cluster nodes. And in the edge node, actually, there are appliances and also households. And in the cluster nodes, actually, is the buildings and also neighborhoods. So cluster nodes communicate the request flexibility which receive from the energy suppliers with the edge node, which are the end users, and ask for the response, and then actually gradually learn from their response and learn the pattern. And also at the same time, learn about the energy flexibility requested by the supplier and communicated with the edge node. And then based on this response and based on the requested flexibility, which are based on a weather condition, prices, and demand and supply, we developed a predictive model in order to understand, okay, when would be actually the best time to send the request to the end users. And at the same time, when would be actually best time for the providing action for requesting the flexibility. We developed also the dashboard in order for the communication with the end users, and also for providing some information about the current status of each appliances, and also about the temporal comfort, and also about the other parameters in the buildings. So in the next slide, I would like to also invite you to watch this video, which are actually more maybe from the perspective of the end user, actually how our solution would be useful for them.
This is Runar. Runar lives in Central Europe and works in a typical high-rise office building with poor orientation and ventilation. For his indoor thermal comfort, Runar interacts with the building's heating, ventilation, and air conditioning system through a thermostat that looks like this. Runar adjusts the thermostat daily, and even multiple times a day. Many things may affect this, including outdoor climatic conditions, but also indoor factors such as glare and noise. Having to constantly adjust the thermostat, or maybe not doing so and feeling uncomfortable, Runar's productivity often isn't optimal, which is where COLLECTiEF comes in. We are designing a software-hardware solution that will allow Runar to train an intelligent control system so that indoor conditions are automatically adjusted. With COLLECTiEF, Runar has to fill in a survey that takes less than a minute of his time, once or twice a week. He can do that through a link on his browser or scanning a QR code with his phone. The results of the survey train the COLLECTiEF control algorithm on the preferences of Runar, considering also inputs such as outdoor weather data and indoor sensor observations. By learning how Runar feels at any given point, the algorithm is then able to predict and automatically improve indoor environmental conditions. Runar now spends a maximum of 2 minutes a week of filling in the survey and letting the COLLECTiEF system take care of the rest. The COLLECTiEF system optimizes indoor environmental conditions and minimizes energy consumption through a human-centric approach, relying on user inputs.
Thanks for watching. So we have several different digital technologies. Actually, we just use the technology provided by our partners. So it included sensors, as you can see here, and also the platform iGateway developed by the G2E Lab, Energy at Work, and R2M, and also the IoT operating system provided by Virtual, and also occupant-centric sensing user sensors provided by the LASTM. So about the business model, actually, we targeting the two groups. The first group is the end users, the occupants. They can use our solution for energy management, and also we targeted the cluster level, the building owners, aggregators, and also energy communities. And also the energy suppliers can also benefit from our solutions. So as I said at the beginning, we are testing our solution in 4 pilot countries located in Norway, in France, in Cyprus, and also in Italy. So in Norway, we have 7 buildings, educational, health care centers, and sports and medical center located in Ålesund city. We also tested our solution in the living lab located in Grenoble in France. And also we have a residential building located in Milan in Italy. And also in Cyprus, we have an office building, laboratory, and educational building in Nicosia. So we promised to reach to 16%, and on average to reduce the primary energy use, up to €3 per square meter annual energy cost saving, and up to 15% increase user satisfaction, and also 24% increase in the demand flexibility. So we are right now actually started just recently the impact assessment. So still we don't know, but we hope actually we're able to reach. And about the main solution, in line with our objective. So we are trying to upgrade the smartness level of the existing building, at least one level. And we also develop a different solution in order to use the actually minimum need for the data transfer and storage, and keep the data analysis at least in the building level. And we tried also to provide a low cost and open source components. And at the end, actually, beside the a whole component and the solution we develop as an integrated package, we are able actually to provide our solution can be used for the energy management in the building site. So as I said, we are in the fourth year of the project, so more or less than 9 months left from the project. So we are right now actually in the demonstration phase, larger scale demonstration phase. So in the next slide, I provide a recap what we done so far, including some information about the next step. So here are some images from the monitoring system installation in Norwegian pilots. We successfully last year demonstrated our solution, the smaller scale location in Grenoble, in the living lab in G2 lab in France. And we almost actually integrated edge node and cluster node, and we are testing our solution, our software in both edge and cluster nodes. We successfully also finalized our user interface and digital dashboards. And right now, actually, we are demonstrating our solution in larger scales in all pilots located in other 3 countries. And about the impact assessment, we initiated from this year, especially about the thermal comfort assessment, energy efficiency, also energy flexibility assessment, and climate resilience assessment. So it depends on our data. And more or less, actually, after we complete the deployment of our solutions in the larger scale pilots, then we are able actually to also perform the final stage of the impact assessment. So about the exploitation and commercialization. So we have a monthly meeting right now. And as I said, we targeted 2 groups. And we had several stakeholder workshops and also with the end users. And we presented our solution so far. And so far, actually, we received a lot of a positive feedback. But we need to have further efforts in order to roll out it to the market. So we are also active for the promotion and dissemination and communication. And today also, in collaboration with SATO, we provided this session. So thanks a lot for your attention. Any question, any comments?
Thank you, Mohammadreza. From NTNU, he's a coordinator of a COLLECTiEF project for the people that have just joined the workshop. Thank you for coming. I would like to leave at the end of the workshop a quick Q&A session.
Sure.
So I invite you to take note of some questions, observations, about the presentations of our Two projects, we have 3 presentations today, and 2 projects presented that are clustering. They are all dealing with the smartness of buildings, specifically non-industrial buildings, so the existing building stock, and also installation systems, devices that are already in place, specifically in buildings. Thank you, Mohammed. So I invite you, your colleague, that is scientific coordinator of COLLECTiEF project from Lund University in Sweden. And he's the Work Package 2 leader that is dealing with the development of algorithms, tools for the COLLECTiEF platform. Yes. Correct. Vahid Nick, thank you.
Thank you. Yes. Okay. Yeah, sure. Okay, so yeah, thank you very much. Thank you, Mohammadreza, for the nice introduction of the project, and thank you all the audience for being here. So I'm talking about the algorithm development for this COLLECTiEF system today. So when we come to this, the main idea here for this COLLECTiEF system is to provide an easy solution, easy to implement, and cheap for buildings that are not very advanced in or very capable of becoming smart. We have limited options of making buildings smart. So we need a technology that is enable enhancing the energy performance of buildings. Meanwhile, it shouldn't be very complicated, and it should be easy to install, and at the end it should become a cheap solution. But most importantly, it should be able to cope with this complexity that we have in urban areas, because we have multiple components like user behavior, weather conditions, variations in all of them, and also different energy users, energy producers, whatever. You have different components that add to the complexity. And these layers of complexity make the energy management at the end very complex. And then most of the available solutions at the time, for example, those that are shifting all the calculations in cloud computational systems or cloud computing, they somehow add up to this complexity that we have in the system, because then you have this, let's say, higher level control. So we want to avoid that. And also a big concern for us is coping with this climate change, how to prepare our cities, buildings, and systems for climate change. Because we know that, okay, with climate change, we will have warmer climate. Meanwhile, we have stronger and more frequent extreme weather events. And these extreme weather events are critical parts of the year or any season that we need to have our systems prepared for. Actually, the energy system that we design for works usually the design that limits that we plan the system is to cope with cope with that extreme events. And then when we add more renewables and when we have this complex system, then coping with those extreme events becomes more challenging, because, you know, for example, when we have a higher share of renewable generation, if we have, for example, cold winter, it means that, okay, there is, for example, in Scandinavia, there is not that much solar radiation. If wind doesn't blow, then you won't have wind generation as well. So, and for example, if you have 40% renewable generation, then yeah, that is a critical situation. Then you need to heat up buildings. So one part that we do is that we, as Mohammadreza mentioned, we assess the performance of our solution against these climate variations or future climate scenarios, or in short, we check how climate resilient is our system. And then when it comes to this energy management, we need some kind of more innovative approaches. There are already white, gray, black box modeling approaches and AI-driven approaches, many of them relying on machine learning and reinforcement learning, which comes under machine learning. But as I said, at the end, many of them are cloud-based, or you have a higher control. You have a strong server that takes care of the control. So to, let's say, come with a new solution, we combine this collective intelligence with reinforcement learning in energy management. So we call it SIRLEM. So let's go step by step. This collective intelligence is that, let's say, where you have these agents helping each other. If it's called each, in this case, each fish is an agent, or in urban area, each building is an agent. So we don't need to have a very smart agent. The brain or calculation potential or computational potential of each agent is limited. But as a group, together they work in a very smart way. They help each other to pass an extreme event. For example, if each shark is attacking is an extreme event, then this group of fish, then together they can pass that extreme event safely without that much computation. They just have a very limited brain capacity, calculation capacity, and it's a very simple signal transformation between each agent. You just, for example, need to move for about, I don't know, 50 centimeters, then you are passed. So we take this concept of collective intelligence, and it makes the system dynamic, and then meanwhile you don't need that much computational power, and then it helps to reach to that adaptive behavior that self-organizes itself during time. And then this reinforcement learning is the brain inside each agent. So if we have fish here, then the brain of that fish is our reinforcement learning algorithm. So the agent learns, and in reinforcement learning is like that. You learn by, let's say, learn the environment and select the right actions by having a kind of rewarding system. And this one also doesn't need that much computation in the system that we develop. So what we do is like that. For example, if we have a DSO, then we transfer a signal from DSO. Let's say it's a flexibility signal or price signal, any signal. Then a signal is transferred to each agent or building, and then inside each building we have this brain, which for us is reinforcement learning algorithm that comes with a device. For example, it can be a Raspberry Pi or any cheap computational tool. So this signal which is transferred from DSO is kind of representation of the environment. So it represents the environmental condition. So then buildings or agents are reacting to that signal. So this is what we do in work package 2 of COLLECTiEF project. This work package 2 has these 5 tasks that I'm not going to read through them, but we have 5 tasks, and mainly is about developing the algorithm and testing that at different levels, at the agent level, or at the edge node calculation, and also at the cluster level. We have tested the algorithm for different cases. For example, is one test case in Norway. So it's an elderly house. Then we have been collecting data and then simulating that, and then simulating that for different future climate scenarios as well. And then also we have been adding renewable sources, buying energy from the grid, and also having several EVs or electric vehicles, then checking how the system performs. Also then this is at the agent level, or let's say building level. In the case of need, we can divide each building. If, for example, this building is a big one, then we can divide each building to different zones, and each zone can be an agent. Then these zones also each zone receives the signal from the cluster level. And then this is the signal distribution at the cluster level goes to each agent. As Mohammadreza told you earlier, we have been testing in different, let's say, environment. The first case was this kind of living lab that we have in Grenoble, and algorithm has been running at least for 1 year. And then when it comes to the inside the building, then the brain you have knows about the control options you have inside the building. And these control options are different. For example, in one building you have maybe 4 units, like you can control the heating set point, cooling set point, ventilation, and, for example, shading. But in another building, you can only set a heating set point. So the good thing with this algorithm, the reinforcement learning part, is that, okay, when you define the options, control options, you don't need to run the environment for it. You don't need to model the environment for it. So it's a model-free algorithm that it learns by doing. So we've been testing that, for example, for some future climate scenarios. Here we look into one extreme warm year. This is the extreme warm year if we do not have any specific control algorithm. This is a typical year, as you can see, the cooling demand. So it's a big difference moving from a typical year to extreme warm year or extreme warm summer. But these are, by applying this algorithm at edge node or cluster node levels, then we can decrease the energy demand, as we see that, considerably. And still we can keep the indoor temperature at the, mostly in the comfort zone. This is the case, the same buildings, but heating demand for an extreme cold winter. So we have 3 months of 3 very cold months during, let's say, 2040 to 2070. That 3 months represent the very cold winter of this 30-year period, okay? And then here also we show that, okay, if we implement this algorithm, the collective solution, we can decrease the energy demand considerably lower than not implementing that. Even we can decrease the energy demand for the heating cases in Scandinavia to values lower than typical conditions. And it's still, the indoor temperature is somehow mostly in the comfort zone. We have been also looking into, we have been trying different signals as the informative signal or as the representation of the environment. Like, for example, we have been using here demand signal, which is kind of flexibility signal that we are using, or price signal. Price signal is very well used nowadays in most of the energy networks. So as you can see here, if this is the typical condition for us and without running our solution, then we come to extreme cold winter. Without our solution, then if we run based on demand signal or cost signal, sorry, then you can see that demand will increase for about 50% and cost for 44%. Then if we apply our solution and using this demand signal, so the energy demand increases only for 24% and cost only for 10%. But if we apply this price signal, we even do better. We increase the energy demand for only 9% compared to typical conditions. And then the price can become even less than typical conditions. So the system is smart, learns how to react in the environment. So for the price signal, we were using the actual price signals, for example, for the last year in Norway. So all in all, I don't go through all the points here. So we could develop a kind of easy solution, an RL-based, CI-based solution that is a model-free solution that doesn't need heavy calculations, and then it can adapt easily to environmental conditions, to new conditions, and then at the end we reach to a synergic behavior in the whole grid. So that's almost what we needed, certainly what we needed in the project, but now we are testing that in some other case studies in 4 countries that Mohammadreza showed you. Thank you very much.
Thank you, Vahid. And you anticipated also some interesting issues that I had to take a note about to ask you some questions, clarifications, but that's interesting. Thank you, Vahid. So this is COLLECTiEF project. Thank you, Mohammed and Vahid. And I invite Vinicius, Goko, sorry, Gogo. Are you sharing the presentation with your colleague? Miracle.
It's the same presentation for Miracle and me,
Professor at the University of Lisbon, you're coordinator of SATO?
No.
Not coordinator.
I'm coordinating the architecture, but not coordinator of the project. Yeah.
Okay.
Okay. So I think I can.
You can stand up and just make sure that it is on because it's for the registration of the work.
Yeah. Okay. That's fine. Okay. So thank you, everyone. So you can sit or here. Okay, so thank you, everyone. My name is Vinicius Cogo. I am coordinating the development of the SATO platform in the SATO project. The idea here to present today is to depict a little bit the current status of the project and what are the main goals and how have we been achieving those goals. Just a brief overview of the project. We are 16 partners from 7 different European countries. The project started in October 2020 and it's finishing by the end of this month. So we are almost closing. We are having the General Assembly today also here in Luxembourg and tomorrow. And basically the idea of the SATO stands for self-assessment towards optimization. So basically the self word here is very important because what we are trying to do is to create an IT platform for the automated self-assessment and self-optimization of buildings. Okay, the idea here is to use and try to improve the real-life building energy use, smartness, and occupancy, comfort, and everything else. And we rely upon very strongly on semantic-based technologies to provide interoperability, like several other projects I have been seeing this afternoon, for instance, several sessions on data modeling, on using ontologies, and we rely upon them. But we try to use this technology to make the building self-controllable, let's say, or to be aware, self-aware, for assessing this, the status and optimizing it autonomously. So basically what we did is we developed a cloud-based platform that integrated several commercial platforms from project partners and other external platforms and external data sources. And we are employing enterprise-level software that is widely used on the industry to implement components that are agnostic to the computing platform it is running. So nowadays we are running on-premise infrastructure, but if we want, we can, in a click, just switch to a public cloud or to a hybrid environment and so on. So the way we are trying to develop this platform is being agnostic to where it is running the processing, let's say. As I mentioned, we are relying upon standardized data models and interface to represent and implement data from sensors. We have been extending ontologies to have the concepts of KPI assessments and services because not all of them or very few of them have some of these concepts integrated. And we have been using these standardized models, semantic models for device buildings and other entities involved in the self-assessment and self-optimization process. Basically, our platform, if we see, is this blue box, let's say here. We have some actors, traditional actors, building managers, building occupants, and everything else. We have the buildings itself with their sensors and so on, and also external data source like energy prices, weather APIs, and so on. Basically, we divided our platform in three main layers. Okay, so this is one common layer. The SATO middleware is a layer for the interoperability part, for preparing the pre-processing data. Many projects have similar layers. We call it here the data ingestion. But as soon as data arrives our platform, we try to harmonize that like in a data lake environment where we have this harmonization, the enhancement, data quality is asserted in this layer as well. So in the end of this part of this layer, we have a very good refined data lake, let's say, with all the data that is coming from all those external entities. Okay? Then we have the blue part of this architecture, which is where we implemented the calculations of KPIs based on this data, and KPIs lead to to enable certain assessments, let's say. And all of this we can call like a brain of the system, where most of the processing happens to prepare data. And then in the green layer, we have both the services that will actuate on the buildings based on the results from the assessments, and also user interface for those actuations that depend of a user on the loop, or that are not only dependent on the assessments directly, but someone decides and then take actions on that. So we have these both scenarios. This is just to expand a little bit, not to have a discussion on every one of those concepts, but from those 3 layers, we have developed more than 25 conceptual components on how to prepare data, how to process data in a generic way, and how to use this data to provide self-organizing, self-optimizing services. Okay? And it resulted in more than 170 components that were defined in this architecture and implemented in the platform. So this is the general overview. Of course, I don't expect you to see the details there, but it's that in this blue part in the left of the blue layer, let's say, is where we have all our definitions of our assessments and KPIs, and also in the green part of our service. Just to have an idea, let me pass. Yeah. So basically, we have these conceptual components, but then each building can instantiate several of them for different rooms, for the whole building assessments and optimizations and so on. We end up having other hundreds of instances of these components. Just to have a few numbers on the current stats of the SATO platform, we have 9 pilots. These 9 pilots sum up more than 8 buildings. Of course, the residential pilots, we are considering each apartment a building, so that's why that number is so big, let's say. And we have more than 60 apartments in our pilots. We have been configuring, and our knowledge model knows more than 450 spaces and zones in these pilots, in these buildings. And we have installed more than 3.3 thousand devices on that. So we have, in a certain snapshot of time, at that time, we were running, for instance, more than 120 KPI instances and more than 104 assessment instances. Just to have an idea, we have the definitions of more than 90 KPIs and more than 130 assessments that can be executed in the platform. This was a snapshot of the current stats at that time. And the current version of the platform itself that controls and actuates and decides what to do has more than 26,000 lines of code, and only the assessments, the implementation of KPIs, and the service has more than 11,000 lines of code currently. What we are doing now, I will pass to Miracle first to present one context-aware application running in our platform, and he will explain to you a very important concept that is this for this self itself in the platform, how we modeled to enable the platform to discover what should be run and when. So he will explain, and then I come back with another context aware and finalize the presentation. Okay? Don't know if you need this. Yeah. Up and down. Yeah.
So greetings, everyone. My name is Miracle, and this is I'll take off from where my professor and my boss left off from. Okay, I'll start off from the basic statistics, but before I continue, I would like to say it's a good day to motivate myself, okay? So the SATO pilot, I'll start with some basic statistics. We have 9 pilots. Within these pilots, we have over 80 buildings, and these buildings have different categories: the residential, the educational, and office buildings. Within those buildings, we have over 450 zones and spaces. And within those zones and spaces, we have over 3,000 devices. However, sorry, how does it go?
No, it's this.
Okay. So each of these buildings, to continue, sorry for that, each of these buildings have different devices that are being produced by different manufacturers or vendors, such as the Excel, Siemens, Shelly, and the Ready. And this poses challenge for data integration. And one of the primal challenges we faced during the beginning phase of SATO project was to build a data model that can encapsulate all the building entities within the platform. So going further, we decided to come up with our primal objective, which is to facilitate seamless data and systems integration through a semantic-based approach, and also to enable automated discovery of assessment and services, which I'm going to elaborate on later. With that said, what are we going to do? These are the 3 things we need to do. We need to represent data and semantics in a standardized manner, then come up with our own context information model that represents how everything is connected within the building, in terms of the building, the systems, the devices, and so on. And also, how do we keep track of the historical data coming from the sensor or the devices. So going further, we decided to adopt technologies. I'll go into those technologies later, such as ontologies, smart data models, and NGSI, the new generation service interface linked data. Then from there, we decided to represent the highly connected knowledge using our context information model, and decided to track historical data using time series databases like timescale DB. Going forward, in terms of harmonization, we decided to use a common approach, ontologies, which is, it provides a formal and explicit representation of concepts within a domain in the form of linked data approach, triples such as subject, predicate, and object to represent the data. Then NGSI-LD, the new generation service interface, we adopted this technology to represent real-life objects in a way that is understandable to humans and computers as well, because they provide a unique URL or URN for each of the entities. Then, because this NGSI-LD can link multiple or combine multiple ontologies, we decided to adopt the smart data model to represent concepts such as, because we didn't want to reinvent the wheel, we need to look at pre-existing ontologies that can model concepts we have. So we decided to model concepts using this smart data model, concepts such as building, spaces, and devices. However, at that time, there was no way to model zones. So we needed to model zone, and in our platform, we had the philosophical intuition of what a zone means. A zone means a virtual space where an assessment can be performed. And in our ideology of zones can be a virtual space within a space or a collection or group of spaces. Going further, with this in place, we created our context information model, which acts as the brain or the soul of our platform, as they provide a knowledge representation of everything within our building, devices, building, how they are connected to each other, and so on. And also for the time series, we decided to adopt the time series database to keep track of the historical data from the sensors. Then in SATO, we decided to, one of our major objectives is to create context-aware application, intelligent systems that can adapt its functionality to the context of the building environment, such as user comfort, for example, which implies how comfortable a user is within a certain space. And with that, we have our second objective, which is to introduce the concept of tasks. Tasks which are involved within the buildings, create task definitions and integrate them in our context information model, and use that to facilitate the autonomous creation of task instances and scheduling for deployment. I know this is confusing at this point, but I'll try to break it down in the subsequent slide. So giving an example, an occupant in a space, he has this convenient temperature bandwidth, and we have a sensor within that space. One of the first things to do is to check the temperature deviation if it's outside the bound of the occupant's convenient temperature. Then based on that, a service can be triggered, maybe to send command to an actuator to open the room to regulate the temperature to suit the occupant. But the message I'm trying to pass in this slide is that there are several computations that are being performed, and they depend on each other. One is checking the temperature deviation within the space, is a computation, and the second one is the service that are going to be performed. So in SATO, we are not only confined for just building, for monitoring purposes, we also want to perform several assessments. And these assessments have many computations that depends on each other. So we introduce the concept of task. And what do I mean by task? Task is any computation or logic that takes information from the context information model, performs a computation, and publishes that result back into the context information model. So task comprises of, in our scenario, task, in modeling the concept of task, we have 4 categories. One is the virtual sensor, which are just basic simple computation. Then a more complex KPI, which computes a new metric. Then we have the assessment, which uses the previous KPI, compares with a reference or a baseline. And then we have the services, which are actions that impact the building. Going further, in modeling tasks, we have many properties, but these are the 3 main properties of tasks, which are first the entry point, which points to a function to execute a task. The second is requirement, what is required as an input for a task to run. Then we have the frequency in terms of when should this task be performed. Then when modeling tasks, we have a generic template outside the context of the building. For example, we have thermal comfort. This is it. Then we have we want to perform a thermal comfort task. We need the requirement to perform this thermal comfort. We need the requirements such as, okay, the temperature sensor, occupancy sensor. Then we have the entry point, which points to a function, and how frequently should this task run. Then this task instance is under the context of the building. For example, the ID points to a space within a particular building, requires points to the ID of the particular temperature that is going to be used to facilitate that task. Then others are the same. The entry point and the frequency is when it should run, whether hourly, monthly, daily, and so on. Then in SATO, we have the concept of the self-assessment framework, which is responsible for executing these task instances based on the requires property. Going forward, I'll give just a scenario. First thing is I'll give a scenario on the same thermal comfort. The first thing is we want to compute an average, simple calculation, average of several sensors within the space. The virtual sensor is a simple task that performs this. Going further, we use the input from this virtual sensor to compute the key performance indicator. The output from the key performance indicator is used to compute an assessment. Then the assessment is used to perform a service that actually impacts the building. Then this is a visualization from our web app that shows what an occupant perceives instantaneously in time, whether he's cold or cool, and sends it to the building manager, and so on. Sorry, there's a mistake here. And this is the results from the assessment, which points to how they feel within certain categories in the building. But going further, we have a major challenge, but I will explain the challenge before I talk about. I will explain the concept of task instance discovery, the same concept. Imagine that we want to perform a service called thermal comfort, right? And this service requires 2 things, occupancy sensor and temperature sensor. And we have a building. Inside the building, we have, like what I'm trying to show here is we have a building with 9 spaces. Now, we go into each of the space and check. Does this space contain a temperature or an occupancy, temperature and an occupant sensor? The first space ticks, yes, it's available there. We can perform a task here. Then the second space has just a temperature sensor. We cannot perform that task here. However, it's a tedious process to manually go through all this to see what task instance can be launched. So in SATO, we introduce the concept of self-discovery, which is an autonomous process whereby we look at the task definition and we look at the task definition and the context information model to generate all the possible task instances that can be launched within a building or multiple buildings. And with that said, I would like to pass it to my professor to talk about the concept of another context-aware applications such as smart readiness indicator. Thank you.
Thank you, Minuk. Yeah, I would just use this slide before passing to the next one, which is I was trying to see so many projects using semantic ontologies and trying to figure out what is different in our project that I could present here. And I think if you have to remember one slide from this presentation is this self-discovery tool, because what we did is all those semantic ontologies and everything that we see everyone using, we can consider that as a domain ontology. And what we created in SATO was a technical ontology that is kind of a meta-ontology that only explains what is a task and what are the requirements of that task, and then mapping these requirements to the domain ontology. Why? Because when we have the current status of a building, we can fetch to see from all spaces, all zones in the building, which are the requirements that I already have accomplished or fulfilled to launch the tasks that depend on that. So if I insert, for instance, two new sensors in a room that there were no sensor there, I install, it starts receiving the measurements, and then if there is a task that depends on two sensors in the same room, the platform automatically launches the KPI, launch the assessment when it starts receiving the result from KPI, and then launch the service to start controlling those sensors or actuators automatically. That's the goal that we have been trying to use this technical ontology on top of domain ontologies. Okay? So I will give another context-aware example, which is, since we are talking about smart readiness in this session as well, I brought the famous SRI. Basically, the idea here, and I'm not an expert from the engineering area, I'm a computer scientist. I'm trying to bring the example of the context of our application here, but basically SRI is a single score to classify the building smart readiness, like an energy label for an appliance. We have a kind of smart readiness label for buildings. And basically it assesses or measures the readiness to adapt in response to users or occupants, to the readiness to facilitate maintenance and being efficient in the operation, and to respond also to grid as events. Basically, we have several impact criteria, and these are influenced by all those lists of technical domains that influence each one of these criteria. What I want to bring here is that usually this type of calculation is done statically. Like we need an expert to go in the building to fill an Excel and to result in a value. And we have these Excel files. In SATO, since we have this part that we are trying to be more autonomous, more self-aware, what we are trying to do here is, first, let's imagine that we already have an SRI of a building, okay? So we have the Excel file. Our partners, Siemens Austria, had created an ontology for explaining the SRI, so they published it. You have the link there. But basically, the idea is we convert those Excel files to a semantically enhanced, let's say, data, where every single category, domain, and impact factor there is described semantically, and then we can insert this information into our knowledge graph, okay? So assuming that we had that before, we can do that, and we have this number for our building, the SRI of our building, where we can use it as a baseline. But what matters here is that with the dynamics that SATO enables, we can monitor now what are the services that are still running and effectively running, what are the requirements for which assessment and everything else. So what happens is that we can have a continuously assessing or self-assessing SRI and comparing with that baseline that was statically measured once. And this self-assessing is based on the status of all currently active sensors, devices, assessments, and services. Because having a service available influences a lot the SRI, right? So we can compare with this baseline. We can, even if we start inserting certain sensors and devices, we start to launch autonomously some assessments and new services instance in those rooms, for instance, which also increases the SRI autonomously. So I don't need to reassess from scratch on those Excel files. I can update automatically and see it reflected in the platform. Okay? And even it can also help in fault detection. If I have some sensors that stop sending data, it will also block or prevent the execution of the assessments. And it will prevent the availability of a service. So it also influences negatively, in this case, the SRI. So that's what we are trying to do, and we have been doing in SATO, try to use this dynamicity to create self-aware towards self-optimizing buildings. Okay? So in conclusion, we have been relying a lot in semantic web technologies, as many. We try to create a technical ontology that maps to multiple domain ontologies. We are using SATO now, but we could use Haystack or Brick or other ontologies at the bottom. Just need to remap these connections. We created this idea of task to enable autonomously instantiating tasks in the building. And this principle we present with context-aware, with thermal comfort as Mirko presented, or SRI, also applies to many other services that we have foreseen in the platform, like fault detection and diagnosis, building state prediction, whole building energy consumption, partial building energy consumption, and working towards systems, control optimization, and others. So this is the main goal and the work we have been doing in SATO. So thank you for your attention and for being brave to stay until the end of the of the conference and the session. And yeah, thank you.
Thank you, Vinicius. Thank you, Miracle. Yeah. Is it Miracle or Miracle? Miracle. Miracle. Milagros. Yeah. Thank you. And okay, let's start. The workshop is over. But now we have the Q&A session, and it would be interesting to have people discussing a bit about this hot topic, you know, because smart readiness indicator is pretty trending, and market opportunities, not only, but also in terms of growing importance of the sustainability of the buildings. I mean, makes that interesting also. We have the EU directives about the SRI. So I would like to trigger some questions, but I will start with Vahid. Sorry, because your name, I took note of it. But you mentioned several interesting things, aspects. And, okay, very simple question. What about the let's say the benchmark or differences between your energy management approach and the existing, the available ones, okay, the typical energy management approach that could be replaced, the conventional ones, by the advantage.
Yeah, we have done that.
And let me continue so that I will just ask once to you. You also mentioned the challenges related to the complexity of the building stocks. So how your approach is addressing this challenge, okay?
So, yeah, answer your first question. Yeah, we are comparing with your typical energy management, both on simulation cases that I showed you, but for example, in the Norwegian case, since we are simulating an elderly house, then the assumption is that, okay, indoor comfort should be always guaranteed. So the energy management is one big aim there is to keep the indoor comfort, indoor temperature at the comfort level. So, but considering that, we were also we could decrease the energy demand considerably, having the indoor comfort and so fulfill it. And then concerning complexity, the major part, the major contribution of the approach is that we have this very centralized calculation. We have agents that are not relying on each other, but they are helping each other. So most of the calculation of all the decision making is happening at the agent level. There is no need for having a higher control or telling the agent, okay, do that, do this. The agent is just being informed about what is happening outside. And then all the decision making is happening at the agent level, inside the agent. So in this case, we keep the calculation and all the computation at the very local level. So we don't need to do this cloud-based computational systems, use them or do any cloud computing. So in this way, we decrease the complexity in that system, energy management system and security.
Thank you, Vahid. But pair with that, I have remaining technical questions, and then I have some more, let's say, related to market and concrete applications. But Vinicius, and the basis of the data model, of the context of SATO, this is also, I think, a difference between what he has said now and the more standardized approach that your tool has. And what's the basis of the data model? Miracle.
So the idea of the data model is to provide a standardization whereby, for example, I have multiple buildings and their representation can be different. And if you want to query the same data across many buildings, it should be seamless, regardless of the diverse representation. So ontology is the foundation behind that to provide like a homogeneous way whereby we can query the same data across multiple platforms. So that's it.
And you have sensors, different devices installed, and how you're dealing with the interoperability, the integration issue. Is that a challenge, or?
It is, and it's a challenge that is common to many other projects that I see today. And I think as a computer scientist, I try to see this challenge as the same problem operating systems have to deal with multiple diverse hardware components. They have drivers that translate from the hardware into the software. And here is more or less the same. Of course, we need drivers to start talking with certain platforms, but many platforms talk using similar technologies. We just need to translate first the syntactic part, like the format they use to the format we use. So it's a driver to convert that. And the language semantically. So to speak the same language in all components, some technology or some fabricants, the manufacturers, they use different names for the properties, so we need to translate to a common one. So I think it is a huge problem. It is a problem we solve with platform at platform. Each platform has a sort of driver that converts things to the common data model that we have. But it's not exclusive from SATO.
Vahid mentioned the complexity of the building stocks, for instance, and sorry, you want to say something?
Yeah, the difference, for example, here we bring here is that we don't need to, with this system, which is very agent-based, we don't need to implement a similar language. It's just a matter of translating that environmental signal, which is, let's say, for example, price signal. If the agent understands the price signal, then it can implement the logic or the algorithm, implement that into its framework. Doesn't need to translate that, or we don't need a unique language among all the agents.
So I think that this approach also, they are different approaches, but probably complementary depending on the applications, the kind of buildings. For instance, SATO is, just correct me if I'm wrong, designed for non-industrial buildings. But, I mean, what are the differences we should take into account in deploying SATO, either in commercial, office, residential buildings, if any?
Basically, SATO has both types of buildings. In non-residential, usually they have way less space zones and sensors, and they are more controlled. But still, the platform works independent. It's just the model modeling is exactly the same. A building is a building and it has devices, has own space and so on. What happens is that for industrial buildings, for instance, we have many more space, many more sensors, many more different platforms. What we do, for instance, we enable receiving bin files. One of our partners is SATO, which has an open bin technology. And they of course, it's not common, as far as I know, that it's not common to have very good bin with all sensors in place or everything else. But if you insert one bin IFC file in SATO, it ingests and populates the knowledge graph based on the space that are reported there, the sensors that are there. So from scratch, we could start with a new building, just insert an IFC file, and let's try to organize that in our view knowledge graph. What happens is, if someone inserts a new sensor, we don't know where is it, and then we also can start receiving data even if we don't know what is it and where is it exactly located. Our interface can ask. So it's different, the level of the complexity in this sense. But for the SATO platform is the same, at least the model, let's say.
One question, but you need to understand the building. You need the model of the building, or not?
No. We translate that into those categories like space, zones, sensors, and that's it. We don't need to.
So what those categories should be known. For example, if you have a building, you should know that this building has, for example, 10 zones.
Yeah, but we translate directly from IFC. So if you can describe that in bin, we can read that and translate. Otherwise, the other solution is start from scratch in the platform, register a new building, and start filling. Okay, I have X zones, I have Y spaces in each zone, and then you start populating. There are interfaces for that. But I think that if you have bin, it's for industrial buildings or large office buildings, it's easier.
Yeah.
Thank you, guys. Mohammed, okay, you have perhaps some more visibility about the whole consortium, your coordinator, you're not, but I will ask the same to you, so stay tuned. You know, we are in the very delicate exploitation phase of the project, okay? So what's next? After the completion of COLLECTiEF, who will be benefiting from these solutions? And among these solutions, are there any immediate output that could be immediately deployed into market? And how? And you know, the Dark2M is always ready to take the opportunity to bring into the market something.
Dark2M is our partner who lead the exploitation and commercialization approach of the COLLECTiEF. So as I said, we started from this year. Actually, we have a monthly meeting about how we can actually deploy our solution at the end of the project. Of course, it's not easy, but since this is like a high TRL projects, innovation action project, so we hope actually we are able to do that. So for that, we have two perspectives. I mean, the first is actually we want to target like energy suppliers, owner of the buildings, energy quality, aggregators, and other players. For those, actually, we had several workshops in different countries, and we collect the feedbacks. We had like a one-day workshop and discuss in details about their challenges, and we present our solutions for them and try to also find like a common terminology with them and understand, okay, what would be actually the next for them also, because some of them has like a long-term strategy, and some of them want to know actually how our solution can be fit with them. So that's why actually these stakeholder workshops were so useful for us, and we also still have some better understanding of here after the project how we can reach out to them again and present our solution with some final result. I think the SATO is in this position right now. And another perspective is about the end users and occupants and so on. In the building level. So as I said, one possibility would be we consider the COLLECTiEF solution as for the energy management. control their appliances and also the householders. And also they try to use our solution in order just to be replaced with the maybe other control solution available in the market. So that's two perspectives, and I forgot the second question you asked.
I mean, it was pretty much the same, but it's about what's next and immediately, you know, after, when is it finishing the project? When is, I don't remember, has it be end of May? End of May 2025. So 1st of June, what will happen?
Yeah, some of our hardware package, for instance, we have sponsors. So the sponsors actually developed during the project. So they had the last LSI, which is an Italian company. They had a similar solution, but during the collective project, we tried to integrate with other solutions. We tried to also improve their reliability and stabilities. So one of the immediate solution can be rolled out to the market is the sensors. So it's already deployed, and we already actually installing our pilots, and we tested, and now it's really ready for the market. So about the software package.
Yes, but excuse me, in that case, you need also to foresee kind of industrial production or something.
I mean, that was not the main objective of the project, because we want to provide integrated package, including software package developed by Vahid and his team, and also the hardware package with the other industrial partners. So we want to deploy actually this integrated cluster node and edge node solution as a one package, but of course there are different components can be rolled out separately. So that's something we are trying to also understand how would be the possibility in order to deploy our solution to the market, not only as a one solution, separate solutions.
Vinicius, what about the SATO strategy?
Yeah, basically, currently we have two different levels. One of them is return to academia or scientific side, like we intend to publish SATO platform as open source, free open source, and also many of the data sets we produce, we also releasing them as free and open data sets. And then
Excuse me, is it an innovation action or research innovation action?
sorry?
What kind of action is that? This is a very high TRL, same? Okay.
No, it is innovation action as well, and it has TRL. And other examples are more related with exploitation by enterprise. For instance, we have SAIP that produces this open bin. They created a tool called Open Bin SATO, where they can present the results of these assessments with colors in the bin in the real time. Other case, the VORT has created an interface to help detecting fail detectors in washing machines they sell, for instance. So there are several applications that are arising from the capability that SATO enables, but the platform itself is not becoming a company or a spin-off.
No. I mean, do you think the maturity level of this solution is that advanced to start thinking about the concrete market strategy, or we need some more research?
No, I mean, all the software we use is industry level, like TRL 6.7. Of course, we had to implement some assessments, and this type of things is the lowest TRL levels at now, let's say, but we can start using that in industry as well. Yeah.
Thank you. Any question from the audience? Thank you. Okay, thank you very much, everybody. I would like to remind you also this is the last workshop session of Sustainable Places. I would like also to remind you that there is a nice opportunity for publications. So since there is nice collaboration, clustering, you have not competing products for what I understood, but they are totally complementary, By 30th of October, you can decide to put together basically the slides, the presentations, and also the discussions we had to submit. It will be a peer-reviewed article, okay? There are information on the website. Thank you very much, and see you next year. So just announcement, there is aperitivo, a cocktail we are offering for a farewell this year, and see you next time, Sustainable Places.